All right, we're in 7.4 now, and this is kind of a continuation of what we were talking about in 7.3, which are operational properties of the Laplace transform. There's three major properties we're going to talk about in this section. And the first one is what happens if you take the derivative of a Laplace transform. Now remember, the Laplace transform takes a function of t and converts it into a function of a different variable s. So we typically are calling that capital F of s. And so the question is, what can we say about this function, capital F of s, if we differentiate it with respect to its variable s? And it's fairly straightforward to do that. So if we differentiate capital F of s, remember capital F of s is our Laplace transform, which is this. We're differentiating this function right here. Now remember, s is being treated like a constant here, and I can bring this derivative into the integrand. That's a consequence of my fundamental theorem of calculus. Once it comes inside, notice the change in notation. It's going to start looking like a partial derivative. And the reason for that is if we're differentiating with respect to s, we're going to be treating this function as a function of s for the purpose of differentiation. Even though when we integrate, we treat s as though it were a constant, we're differentiating with respect to s, so it's being treated like a variable here. T is also being treated like a variable because we're integrating with respect to t. So now we have to think of this as a function of two variables, which is why a partial derivative is necessary here. If I were to differentiate this thing with respect to s, remember f of t, being a function of t, has no variable s involved in it, so it's treated like a constant here, and the derivative would end up looking like negative t times e to the negative st f of t. That's what this partial derivative would look like. We could bring the negative out. You can see the t appearing here. And this thing still looks like a Laplace transform, except the function that we're using in our Laplace transform is now t f of t. So this can be written as negative Laplace transform of t f of t. Okay? Now, suppose we wanted to take a higher order derivative. Well, we can continue differentiating each new derivative in that process. So, for example, let's suppose I wanted to determine let me get back here. So this is what the Laplace transform of t f of t ends up being. It's the negative of the derivative of capital F of s, the Laplace transform of just f. If I wanted to find the Laplace transform of t squared f of t, for example, I could rewrite t squared f of t as t times t f of t. And now what this is similar to what we have here. It's t times a function of t times a function of t. So according to this step right here, if we trace this back to the beginning, this should equal negative the derivative of the Laplace transform of this function, which would look like this. But we've already evaluated the Laplace transform of this function in the previous step. It was equal to negative dds of capital F of s. And so now what we have is the negative derivative with respect to s of the negative derivative with respect to s of the Laplace transform of f of t, which is the second derivative with respect to s of our Laplace transform of f of t. And you can continue doing this for as many derivatives as you want, and you'll notice it creates sort of a general pattern. And so the general rule for taking the derivatives of these transforms is this. For any positive integer n, if we want to evaluate the Laplace transform of t to the n times f of t, it's equal to negative 1 to the nth power times the nth derivative of capital F of s, where again f of s, capital F of s, is the Laplace transform of just f of t by itself. Okay? And the negative 1 to the n power indicates that we're having this alternating, negative, positive that's occurring here. So let's use this. I'd like to find the Laplace transform of t sinh of 3t. And in order to do that, I'm going to write this right here, t sinh of 3t. So this fits, fits this form where n is equal to 1, t to the first power. So this will equal negative the derivative with respect to s of the Laplace transform of just sinh of 3t. Okay, and we have a table that gives us this, the Laplace transform of sinh of 3t. This would be equal to 3 over s squared minus 3 squared. Okay, and that's equal to 9 there, so we're going to go like that. I can differentiate this using either the chain rule or the quotient rule, but the differentiation that you can verify this should come out to 6s over s squared minus 9 squared. Okay, so it's not the only way that we could have evaluated this Laplace transform. We could have done this using the definition of the Laplace transform, but the idea behind these operational properties is to give us a shortcut to evaluating the Laplace transform of certain functions, or functions that take a specific form, without having to do all of the integration by parts and stuff that you would normally have to do when evaluating Laplace transform. Excuse me. So let's now apply this to solving a DE. We want to solve this first order DE. Y prime minus y equals t e to the t sine of t, and we have the initial condition y of 0 equals 0. And notice this hint here. Hint, the Laplace transform of sine of kt minus kt cosine of kt is equal to this expression, 2k cubed over s squared plus k squared quantity squared. So the fact that that's showing up as a hint means we will most likely need to use that somewhere, so we should expect to see an expression of one of these two types showing up at some point. But the question is, where did this even come from in the first place? Well, although you could evaluate this Laplace transform directly, nothing in the problem, you'll see, nothing in the problem is going to hint that you should do that. So the question is, how would you even know to use this? And the answer is that this comes from a much larger table of Laplace transforms that appear in your textbook. If you go to Appendix C, I'll even write that here, C, Appendix C in your textbook, there's a long list of Laplace transforms of various different functions. And in the problems in your homework assignment where you're using this, it'll actually tell you in the instructions, use the Laplace transforms in Appendix C as necessary or as needed. So you'll want to go and take a look at that. Up until this point, we've been using that much smaller table in 7.1, but now we're going to need to access more Laplace transforms. So I would have advised checking that section out. Okay, so I'm going to solve this using Laplace transforms. I'll take Laplace transform of both sides, and we're going to get this. Laplace transform of y prime minus transform of y equals the Laplace transform of t e to the t sine of t. Okay, and notice what we have here is the Laplace transform of t times a function of t. And so this is where we can use this theorem up here. Okay, again, it's t to the first power, so in that theorem, it's like the case where n is equal to 1, just like what we did before. This should be equal to negative the derivative with respect to s of the Laplace transform of e to the t sine of t. Okay, however, now I have a Laplace transform of e to the t sine of t, and we recognize this from the previous section as a translation on the s-axis. So we can write this differently as well. This is the same thing. Let's see if I have space here. Negative d ds of the Laplace transform of just sine of t, and the coefficient on that t is a 1, and so this takes s and substitutes in for s minus 1. Okay, so notice what we did. we had a relatively complicated looking function on the right-hand side of this non-homogeneous equation, and we're using these properties to continually simplify the function that we're taking the Laplace transform of. Rather than put that directly into the definition of the Laplace transform, which would be an awful integral to have to do, I can start peeling away factors of this thing using these theorems. And so now we're at a point where we know exactly what the Laplace transform of sine of t is, because we have that in our table. So let me take this down to the next step here. So let's see, this is the Laplace transform of y prime, which would equal s y of s minus y of 0 minus Laplace transform of y, which is capital Y of s. Our initial condition says that this is equal to 0, so that'll end up canceling out. What about on this side? What's the Laplace transform of sine of s? Let me include my derivative there. Negative d, ds. So the the Laplace transform of this guy would normally look like k, where in this case k is 1, so 1 over s squared plus 1 squared. So 1 over s squared plus 1, except we're substituting an s minus 1 in for that s. And so now what we have is 1 over s minus 1 squared plus 1 squared, which is just 1. Okay? And I can take this derivative and also apply that negative there. And what this actually ends up coming out to when you take that derivative is 2s minus 1 over s minus 1 squared plus 1 quantity squared. Okay? Let's do a little simplifying. So on this side, I can factor the y of s out, leaving me with s minus 1 equals 2s minus 1 over that denominator, s minus 1 squared plus 1 quantity squared. And notice if I were to divide both sides by s minus 1, it'll cancel that s minus 1 out. So I'm left with this. Y of s equals 2 over s minus 1 squared plus 1 quantity squared, which, if you notice, is the same thing as this, 2 over s squared plus 1 quantity squared, where my s will end up with an s minus 1 substituted in. Okay? Now we're at the point where I would normally be taking an inverse Laplace transform. And this function right here, although it resembles some of the things on our table in section 7.1, doesn't actually match anything specifically, and it's because we're squaring this denominator down here. However, this is where our hint comes into play. So compare what we have here to what we're seeing here. 2k cubed over s squared plus k squared quantity squared. If we set k equal to 1, that's what we end up with here. And so what that implies, according to this hint here, is that the Laplace transform of this guy is just equal to sine of t, remember k is equal to 1, minus t cosine of t. However, we're also seeing a translation on the s-axis, and from our theorem in the previous section, we know that that Laplace transform will have to be multiplied by a factor of e to the 1t. So this all implies that y is equal to e to the t, again, that comes from the translation step here, times this guy where k is equal to 1, sine of t minus t cosine of t. And that's our answer. Okay? All in all, not too bad. And again, the idea here, notice how much less work we had to do here than if we were to try and do this directly, you know, using the definition of the Laplace transform. That's the entire idea behind all of these properties. Okay, so derivatives of transforms, what we talked about on the previous page, that's the first operational property that we wanted to talk about, and I said there were 3 in this section. The second one is something that we call the convolution theorem. So we have to define what we mean by convolution. And this is an operation that you can perform on two functions. We call it a binary operation, something that you perform on two inputs. And it's used a lot in differential equations. We're only going to see it a little bit in this class, but if you continue taking more and more courses in this subject, you would see the convolution appearing more. So this is a very important operation for higher mathematics, and we're only going to do a little bit with it here. But the convolution, if you have two functions, f and g, that are piecewise continuous on the non-negative real numbers, so the interval 0 to infinity, the convolution of f and g is defined this way. We use this star notation to denote a convolution, and it's equal to the definite integral from 0 to t of f of tau g of t minus tau d tau. So the tau, the Greek letter tau here, is sort of a dummy variable of sorts, because once this integration is performed, this t will be substituted in, and what we end up with is a function of t. So basically you're taking two functions of t, f and g, and performing an operation on them that will produce another function of t. Before we do any examples of evaluating a convolution, we need to talk about a couple of properties of it. So for one thing, the convolution operator is commutative. Your book tells you that it's commutative. It says you can prove this as an exercise, and then it doesn't show you how to do it. I'm just going to do it right here. It's fairly simple to show. You just use a substitution. So if you set u equal to t minus tau, so that du is equal to negative d tau, then the convolution f of f and g is given by this integral. That's the definition. And then look at where your substitution is going to come into play. So t minus tau is equal to u. We're going to substitute a u in here. D tau would equal negative du, so that d tau becomes a negative du. And then this tau right here, if I solve for this tau by adding it over and subtracting the u, I get tau is equal to t minus u, so that tau becomes t minus u. Okay. Then if we plug our limits of integration in for tau here, because that's the variable that we're integrating with respect to, t gets plugged in, t minus t is 0. 0 gets plugged in, t minus 0 is t. So it's kind of like the limits of integration trade places with this substitution. Now what I'm going to do is use the negative from this du to switch the order of integration. Remember, that's a property that you talk about in Calculus 1. Putting a negative in front of a definite integral switches the order of the integration. And so that's going to eliminate that negative and integrate with respect to, or integrate from 0 to t again. Once we do this, I've also rearranged the factors in this product here using the commutative property of multiplication. And now what we have is what the definition of the convolution of g with f would be. So this shows that you can take a convolution in either order and it's the same thing. It's commutative. Okay? Now for our purposes, the convolution is extremely useful when applying Laplace transforms because it turns a Laplace, it takes a, it's how we handle products of Laplace transforms. That's what I'm trying to say. So basically, if f and g are piecewise continuous on the non-negative reals, and they both have to be of exponential order as well. Remember, we talked about that back in 7.1. Then the Laplace transform of a convolution is equal to the product of the Laplace transforms of each function in that convolution. So transform of f times the transform of g. Okay? Now, I'm going to just give you a fair warning here. The proof, although it's not excessively long, does actually assume some familiarity with double integrals, which is Calculus 3. Calculus 3 is not a prereq for this course, but we've used some Calc 3 with partial derivatives and whatnot. We're going to reference double integrals here. If you haven't taken Calc 3, don't worry about it. You don't need to know this proof in order to use the theorem. It's just, I want to make sure that we go through it at least once. So let's start by finding the Laplace transform of f and the Laplace transform of t, which we're also going to be calling capital F of s, capital G of s. This, by definition, is the Laplace transform for each one of those. And we're using different variables, tau here and beta here. Now, if I were to multiply these two things, capital F of s times capital G of s, because that's what's appearing in the theorem up here, then that would be the product of these two integrals. Because we're not seeing any betas in this integral and we're not seeing any taus in this integral, these can multiply together to create a double integral, and that's using a property of double integrals that we talk about in Calculus 3. So here's the step where if you don't know anything about double integrals, you can just kind of tune me out for the next minute or so. Once you multiply things together and combine some like terms, notice what we can do is split this into a different product of integrals here by taking the f of tau d tau out into its own integral. Okay, and again, this is using a property of double integrals that you would have covered in Calculus 3. So now it says holding tau fixed, we're going to let t equal tau plus beta. So this is a substitution that we're going to make. And when we say holding tau fixed, what we're talking about is treating tau like a constant. And really that's only happening over here, which is okay because we're not integrating with respect to tau. So we're thinking of tau as a constant here, setting t equal to tau plus beta. dt would equal d beta in that case, and that simplifies this integral a little bit. The tau plus beta here becomes a t, and this beta right here would be equal to t minus tau. So that's going to make a substitution right there. Okay, so right here it's referencing a figure that's in the book. This is copied out of your book, obviously. I didn't put the picture of the graph in here, so you can look at that in your book if you want to. But where it says figure 7.4.1, I'm not showing that here. F and G are assumed to be piecewise continuous and they're of exponential order, and this is enough to say that we can change the order of integration here. And so what we're going to do here is take a look at that product once again. Capital F of S times capital G of S is equal to this product of integrals, and what we're doing is we're swapping the f of tau and the e to the negative st, so you can see where that swap takes place. And the dt and the d tau are trading places as well. That's what it's talking about by changing the order of integration. Again, that's a Calculus 3 thing, so this is going to be confusing if you haven't had Calc 3. Okay, evaluating that integral directly, this guy in here is the convolution of f with g. Okay, and so we evaluate this integral first. That's what these curly brackets are showing. And this being the convolution is now being multiplied to e to the negative st and then integrated from 0 to infinity, which is the definition of the Laplace transform of this function, or the Laplace transform of that convolution. So this proves that theorem. And again, if that was difficult to track with because you haven't had Calc 3, don't worry about it. You just need to know this theorem, okay? We're going to use that theorem on the next page here, but I'm going to do that in the next video.